Yeah, no time like the present.
Okay, so hello everyone, and it is a pleasure to welcome Alec for this talk, and very much thanks for waking up early for this talk. So go ahead, Alec.
Okay. Thanks, Ketan, for the introduction, and glad we were able to bridge the time zone gap. It's about 6:30 in the morning here, and I had to actually do a little bit of Googling to realize that it's 5 in the evening there. So this is the end of everyone's workday. Glad to be capping it off before the weekend. So I'm Alec Koppel. I'm a research scientist at the U.S. Army Research Laboratory, which is in the Washington D.C. area. And I know K10 from some years back because actually his PhD advisor is my PhD advisor's advisor. So we are sort of in the same academic family. And his student Amrit and Rishi have come to intern with me at the Army Research Laboratory at various points. So I'm going to talk about some of the work we've done together and some of the work we haven't done together. And the theme of today's work is machine learning as it pertains to robotics and autonomy, and basically how does some of the challenges that we face in autonomous vehicles sort of upend the typical industrial machine learning pipeline. Okay, so good. So to start off, let me first try to switch to active speaker only view. Somehow that's only showing K10 and not me. I'm not sure why that is.
Oh. Maybe you can turn off your video. That will be easier also.
Oh, let's see. Yeah, okay, I'll just do this. Okay. So good. So in particular, let's just do a quick overview of how does machine learning work today. Basically, you have a very powerful computer or access to some server farm far away, and you wield those computing resources in order to crunch large amounts of data. And in doing so, you train a very sort of complicated multi-layer statistical representation, such as a convolutional neural network. And this paradigm has really revolutionized the fields of computer vision, natural language understanding, and various others. More recently, video games and sort of a game reasoning. So I'm really focused on how to make machine learning useful for autonomous systems. In particular, the autonomous systems envisioned by the US Army are required to operate in what's called multi-domain operations. And what that means is they envision these vehicles as needing to operate in situations where data may be coming from multiple sources. It might be coming from potentially multiple, might be generated from a non-stationary generating process, and there might be some enemy or adversary that a decision maker needs to reason about. So I'm going to say relatively less about the diverse and contested aspects, and what I really want to focus on today is how to deal with the dynamic part, and how to particularly train good machine learning models when you have data that is arriving in an incremental or streaming fashion. Okay, good. So before I go into more detail about that in particular, I just want to mention there are some overarching challenges that arise in modern autonomous systems. I think one is how to represent uncertainty succinctly when you have streaming data. And this question comes about in all sorts of problems like semantic segmentation, or just trying to put confidence intervals on some time series data. For example, would be like when a hurricane is set to hit the coast of Florida, and you want to know, well, what's the likelihood that the trajectory is gonna bend to the left or bend to the south or the north. And there are questions about when the decision one needs to make may belong to a very high dimensional space. For example, in the context of if an autonomous vehicle is equipped with a robotic arm, then the configuration space of that arm may be very high dimensional. But if we're also looking at some of these sort of like command and control or sort of like strategy type situations, then like where you need to send this or that Hello, can you hear me? Right, I guess there was some problem with the internet. Sorry about that. Anyway, so these four.
Can you hear me?
Yeah, can you hear me now?
Yeah, it was a long problem for a few minutes.
Yeah, there was some problem with the internet on my end. Don't get me started about that.
Continue.
Anyway, so these four overarching technical challenges roughly correspond to a few different research areas that I've focused on in recent years. So the question of how to represent uncertainty succinctly, that is something that I've worked on in the context of Bayesian and nonparametric inference. The question of how to solve problems where the decision space is very high dimensional or complicated is roughly corresponds to the question, to the research area of reinforcement learning. And when you have geographically dispersed autonomous vehicles, this corresponds to the area of decentralized systems. And I think that the time varying optimization research thrust is sort of self-explanatory. And so so before I tell you which of these I'm going to focus on today, which you probably already gleaned from the title of the talk, I just want to explain a little bit why is it that I personally believe that Bayesian and nonparametric inference is a very compelling area, and how innovations in it sort of undergird improvement in all of the rest of them. So let's go a little bit into the problem of supervised learning, which is a very common framework for machine learning. And in the context of robotics and autonomy, it can be used to formulate problems such as localization. You want to have a robot figure out where it is in its environment. You can frame mapping in this way. You can frame system identification. You can frame various forms of object recognition and classification in this manner. And but you know, the rudimentary examples are regression, support vector machines, logistic regression, and so forth. So in the supervised learning problem, what do we try to do? Well, we try to find some function that belongs to some function class to minimize your loss. Okay, and this loss, capital L, is written as an expected value over some data x, y, or you can think of as these are random variables, and realizations of which are your training examples. And it's an expectation over some instantaneous loss, curly L, which is small when f of x and y are close. So you can think in the context of regression, you would just say that L of f of x comma y is just the difference between f of x and y squared, for example. Okay, so you know, you might ask, well, which hypothesis class should we choose our function to belong to, right? So depending on our choice, we might get a linear statistical model, like y equals w transpose x, and then you're just optimizing over the parameter space associated with this vector parameter w. In the case of linear regression or classification, you just compute the sign of this inner product. But you could also choose f to be an element of a non-parametric function class or define some convolutional neural network. So I think it's really important to ask, how should we choose this function, and when and why? And so I'm going to sort of illuminate this trade-off a little bit. So if we choose our function f to be just this inner product, as I mentioned, well, then this defines a stochastic then the supervised learning problem defines a stochastic convex optimization problem. And because of the theory of convex programming, basically we can solve it to optimality using first order methods. But the point is if you do that and you try to apply it to a data set of interest, you observe things like, so this is some attacker detection problem in a computer network. This is from some KDD data set. What you observe is that you deny service unnecessarily to like 30% of users, and you fail to detect like 10% of attackers. So even though we solve the problem to optimality, we don't actually obtain performance that's useful in practice. So this sort of illuminates the trade-off between solving problems that can be solved easily and whether they actually are useful to us when it's time to quote, deploy them in the wild. And now, on the other hand, if you choose some complicated statistical representation, which is an inner product between some parameter vector and some learned signal representation, you can basically think of this like an autoencoder. And then you use this to, for example, try to extract visual features from, this is the camera on one of our autonomous robots at ARL called a Husky. And so you can use this to do visual feature extraction, and then based on visual features, you compute this inner product, and you can try to forecast, for example, the unmodeled kinematic errors, the unmodeled kinematics of your system model, because like modeling, for example, friction associated with grass or like slip associated with ice is sort of like intractable for computing a controller in real time. So you have these modeling errors, and you can use visual features to predict them. And here we overlay the actual experienced trajectory of the robot. The actual kinematic disturbance experienced by the robot. I think that's the green here, and the blue is our predictions. You can see that they match pretty well. But so while it's working well in practice, unfortunately, what I'm not saying here is that the amount of man hours required to actually produce this plot, and the reason that doing so challenging is related to the fact that you have non-convexity, and so actually getting these autoencoders to converge to something meaningful is very non-trivial in practice. So this sort of illuminates a trade-off between like how can we define a statistical representation that gives you good performance in practice in terms of statistical accuracy, but is actually also either easy to train or the optimization procedure on the back end is provably stable in some sense. So I think this trade-off is sort of fundamental, and the kernel methods framework offers a very compelling potential path for finding a happy medium. So what is kernel method? Well, you start by assuming that your function f of x is a linear combination of some kernels evaluated at your training data. So here these xn's would be like your feature vectors in practice, and x is like your test point where you want to make a prediction. And so you say that your function is a weighted combination of these. And what's the idea of this? Well, the idea is that you want to represent some arbitrary nonlinear function, and you say, how can I do that? Well, I can do that with some basis functions, and as I add up more and more of them, then I represent my arbitrary nonlinearity. And this can be made precise, but there's some sort of mathematical similarity between this framework and a Fourier series. So one canonical choice of kernel, I should mention, is a Gaussian, but you can also select polynomials or sinc functions or others. And so now I want to just sort of present my main, let's say, editorial on these relative trade-offs. So hypothetically, what we'd like is methods that are very statistically accurate, like convolutional neural networks, but we wish that they could be solved to optimality, and therefore define some. Therefore, their training could be associated with some Lyapunov function that guaranteed one-step stable improvement in the face of new data. But unfortunately, non-convexity makes this impossible, and non-convexity is inherent to most neural network training. But there are some intermediaries worth mentioning. Of course, generalized linear models. These are models that define convex optimization problems. Therefore, we can solve them to optimality. They are pretty simple in practice, but unfortunately, they fall short in terms of accuracy. So that's why I think that Bayesian and non-parametric methods are an interesting potential path, because, but unfortunately, they exhibit something called the curse of dimensionality, which is basically that they define a statistical representation that retains every data point from the past. So I'm going to get into a little bit why that is, and then I'm going to explain ways to define some very specific projection operators that overcome this issue. And so then the goal of this talk is really about making these Bayesian and non-parametric methods more computationally efficient in the incremental or online setting. Okay, good. Any questions so far?
Any questions in the audience? I think you can continue.
Good. Right. So let's talk. So let's dig a little bit into more detail about Bayesian and non-parametric models and how one might go about training them. So we begin by writing out the stochastic gradient iteration on our expected or population cost, and that has this particular functional form. You can apply the chain rule to this latter term to derive the fact that your update in a function space is basically the function at the previous time scaled by some coefficient, and then this scalar component of loss forms a coefficient for the kernel evaluated at the most recent training data point. So that's interesting because it implies that, as I previously mentioned, the functional update defines an update in parameter space, where it's associated with a data matrix of growing size, right? Every time you retain the kernel at the most recent training example, or sorry, feature vector. And then you have an associated weight vector, which is growing in the sense that the weight vector is what it was before when it's appropriately downweighted, but then also associated with this scalar component. So then what you have is that at time t, your function is a weighted combination of everything that you saw in the past. Okay, so this is a well-studied problem where maybe it's given some flamboyant language called the curse of kernelization. And you might ask, well, how do people deal with this in practice? Well, you can just ignore the complexity and analyze the statistical consistency of your estimator FT to, the population analog F star. That is done a lot in the sort of older statistics literature. More recently, people have produced proposed various forgetting factors, which just say, well, why don't you just drop old points, or maybe you can keep a windowed memory and like try to project the function onto the window of a fixed size. And there are also ways to consider probabilistic approximations of the kernel itself. Those are called the Fourier features. So all of these are potential fixes, except you can show is that if you have a fixed dictionary size, then at least experimentally, it's very hard to figure out how many points you need in advance. And this can actually cause divergence. And so why might this happen? Well, you have your function update at time t. You compute the stochastic gradient that causes the complexity to increase. And then you're always projecting onto some subspace of a fixed size. And the point is, you don't actually know whether this subspace of a fixed size is close to your current iterate or not. So you could think. Let me try to reason by metaphor here. It's like you're going about your daily life and you're always asking, is this event similar to something that to 3 events that I've experienced before? And the answer may or may not be yes, but if you're always asking it, like there's going to be a point where the answer is definitely where the event you're currently experiencing is definitely not similar to 3 events you've experienced before. But if you ask, is there any similarity between what you're currently experiencing and anything you've experienced before or anything close to what you've experienced before? Well, the answer to that maybe gives you some additional descriptive flexibility. So that's what we're after in defining this augmented projection step. And so before we go there, I just want to give a little like a visual of how does projecting onto the wrong subspace potentially have implications for the training procedure. Well, so if this red one is like your full stochastic gradient iteration, you know, because of convex optimization theory, eventually you're going to flow to the bottom of this bowl. But if you project onto subspaces that are maybe very far from your true gradient step, then after a while, these errors are going to accumulate. And you want her to somewhere that is not necessarily useful. So what to do about this? Well, let's delve a little bit into more detail of the update in order to define this projection step. So at time t, we can write at time t plus 1, we can write the stochastic gradient step as we had before. But now, instead of assuming that we're going to be keeping everything from the past, we're going to assume that we're going to keep some active set or dictionary of past points. So that means that, you know, when we compute this update, then we append the newest point, like so, and we append its associated coefficient, like so. Okay, and so all we propose doing is replacing. Let me put it here. We propose replacing the projection onto the subspace of fixed size, right? You can think that's what like your autoregressive model or fixed retrospective memory windowing will do. So we're going to replace that subspace with a dynamically chosen one, and we're going to do a projection onto that dynamically chosen subspace, where this notation h sub dt plus 1 just denotes the span of some kernel evaluations at past points. These bold dn's are, you know, are selected from the history of past from the past training feature vectors. Okay, good. And the very next question should be, well, how do we select these subspaces? Where do they come from? Well, they're going to be. Let me go into the geometric intuition for that in a little bit. But for the moment, you can think it's possible to do some sort of greedy compression technique where an oracle gives you some function that is epsilon close to your current function, but is lower complexity, and that oracle ends up defining a subspace of your function class that is easy to compute projections onto. Okay, so with that sort of epsilon projection defining some modification to your gradient step, then what you can show is that if you set this epsilon threshold to be related to your overall algorithm step size, then the overall function class converges to some small neighborhood that depends on the step size. And interestingly, the memory of the resulting function is finite. So what we're saying is now you can have some, you know, eta close approximation of some infinitely complicated function f star, but with finite memory. So I think it's important to underscore here that this f star has infinite complexity. So what we're saying is we're getting close to the infinite complexity one, but with finite memory. Oh, this did not compile correctly. So let's just, let me just skip that and go into the geometric intuition. So the underlying reasoning for this update is kind of what we already saw for the fixed subspace projection scheme, except now these subspaces are dynamically chosen. And the way they're dynamically chosen is as follows. So you start with your function at time t, you compute your stochastic gradient, which causes the complexity to increase. Now, what we're going to say is we're going to fix some epsilon neighborhood in your function space, and we're going to compute a greedy compression according to this orthogonal matching pursuit. And that's going to yield a lower complexity function that is guaranteed to be epsilon close to our true gradient step. So what we're saying is we're going to cause some epsilon error in our gradient update in order to obtain a lower complexity function. So this dictionary is guaranteed to be guaranteed to have complexity that is no larger than our current one, and same with the coefficient vector. And so by doing this sort of greedy compressions on the fly, we can construct projected gradient directions that are always close to the unprojected ones. So that's a sort of like geometric intuition for what's going on here. And the previous slide was just showing that mathematically this actually works. This actually works well. And so going back to our contour plot of the expected cost, whereas our red is the stochastic gradient step iteration, which is converging to the global minimum, and this orange one is the one that's being projected onto subspaces of fixed size and may eventually wander away from where you'd like it to go. By ensuring that the gradient, the projected gradient updates are always epsilon close to the unprojected ones, then this blue trajectory ends up somewhere close to the red one. At least that's the intuition for what's going on. And so the interesting thing is that now you can use these kernelized this online training of kernelized regression functions to fit nonlinear statistical models of various types. So here is a toy data set that is taken from this Trevor Hasty work. And I think it's an interesting data set because it's not linearly separable. Clearly, right? There are 15. Each of these different colored clusters is a Gaussian distribution with some randomly set variance, and the means of these clusters are randomly set. Each color is associated with a distinct class, and it's basically a multi-class classification problem. So you could solve this using multi-class SVM or logistic regression or the cross entropy loss or whatever you want. But if you try to use a linear statistical model, it will terribly fail, right? Because I mean the decision boundaries is terribly nonlinear. And I think more importantly, actually, the data, it's impossible to classify this data perfectly because clearly the blue and the green overlap, and so do the orange and yellow. So this is the sort of thing that happens in practice. And so if you run this algorithm, which with this dynamically selected projection scheme, which we call parsimonious online learning with kernels, what you end up with is kind of optimally compressed nonlinear regression functions that retain only statistically significant data from the past. So these bold black dots are the retained feature vectors from your data set. These grid points denote the classification decision in the particular area, and the curved black lines are the decision boundaries. So this is what Polk will give you, and so you can sort of corroborate. This didn't compile correctly. Sorry about that. So what you can sort of corroborate this pattern of being able to converge to some epsilon neighborhood, but so clearly the objective function is converging to some small value, and what you observe is a trade-off between how you select this epsilon parameter and how much complexity the function requires, as well as how close to the global optimal are you going to end up at. So let me rewind a few slides and go back to this figure that didn't compile completely correctly, but this is for our toy data set. So what you'll see is that for some fixed value of epsilon, Polk will converge to some small population risk, and it will be associated with a model complexity of 16 points. That's what we observed in our little in our decision surface plot. But if we fix the complexity of all these other compression schemes at 16, then it's clear that their loss functions sort of diverge to some random place. And so that's interesting. And I think what you would observe if this plot down here was not cut off is that initially the complexity goes up and then it levels off to a constant. But now, because we're optimizing over a much richer function class than just linear statistical models, then minimizing this objective function actually does translate to good statistical accuracy, at least for this toy data set. The story gets a little bit more complicated when we try to go to data sets like MNIST or Brodats textures, where you need much more complicated models that end up retaining like 2,000 points or maybe 500 points, depending on your choice of epsilon, in order to get good complexity. But the point is that the algorithm will automatically select which points during training are needed for a good statistical representation. Okay, at this point, I think it's reasonable to stop for any questions. Are there anything unclear? All right, then I will press on. At this point, I want to delve a little bit into what are the sort of merits and limitations of supervised learning, and why it's also useful to study Bayesian inference. So in particular, if we select our statistical model F to be the minimizer of this population cost, well, that's great in the sense that now we have done the best we can do over the given data distribution. But it's interesting to note that this framework maps feature vectors to some point estimates, white hat. In particular, like you start with a given X, and then you look at its image under your estimator F, and that gives you your estimate, right? Y hat. And this is fine if all we care about is deciding like apple versus banana or safe versus unsafe. But the real world often is much more nuanced than that, and things often exist in shades of gray. And so I think that Bayesian inference is interesting because it allows you to try to make precise the notion of shades of gray with a probability distribution. So rather than saying, oh, I'm just going to assume that y hat is, has some value A or B, instead I'm going to look at its entire likelihood conditioned on past information. And so far we were only talking about mapping features to targets, but in autonomous systems, but when we go to the question of how to track the full distributional estimates across time, when things are linear, this can be done pretty effectively with variants of the Kalman filter, and so probably most in the audience have already learned about that in some undergrad control systems class. Unfortunately, though, when you make no linearity assumption on the relationship between X and Y, then there's some more, let's say, interesting or technically challenging questions that arise for how to represent your distribution efficiently. In these nonlinearities happen all the time when you experience things, when you study things like legged locomotion or various forms of localization and mapping, when you have the presence of like urban clutter or interference channels and stuff like that. And they also come up in finance. So when you have a nonlinear relationship between X and Y, then what to do? Well, the sort of the technical foundation for all of the more recent work on Bayesian neural networks is basically based off of Gaussian processes and particle filters and their approximations, or at least a significant proportion of it. And similar to what we experienced with kernel regression, they exhibit the same intractable memory growth with streaming data in the sense that they define a statistical representation that retains everything from the past. So in particular, if you crack open your textbook on Gaussian processes and you look at chapter 2, you'll observe that there is there's an update for a conditional Gaussian distribution at the next time upon the basis of all the data you have currently, and the most recent training example in which you compute a conditional mean and a conditional covariance. And these conditional means and covariances, the specific formula is not that important. The important thing is the the factors that I've highlighted in blue, which are also terms that appear in kernel regression, actually. So this term is called the empirical kernel map. This blue guy here is called the kernel matrix, and basically this kernel matrix is a Graham matrix of kernel evaluations over everything that's happened in the past. So similar to what we had in sort of vanilla kernel regression or classification, in this Bayesian setting, we similarly have this curse of dimensionality, because every time we get a new point, then we need to store it in order to compute this kernel matrix. So this is a technical challenge that people have also thought about a lot in the context of Gaussian process approximations over the past, let's say, 15 to 20 years. And so what's going on with Gaussian process approximations? It turns out that the story is very similar to what we experience in kernel regression. In particular, you have some Gaussian process posterior in time t. You compute the a posteriori update in time t plus 1, which causes you to the kernel matrix and empirical kernel maps dimension to increase by 1. And then basically what people do is they say, well, I'm just going to project that onto a subspace of Gaussian process models of fixed size, and hopefully that'll work well. And I would say there's been a ton of work based off of this central idea, and it sort of started with this work from Seeger, Williams, and Lawrence, and Snelson and Garamani, but and Titius, but there's been a ton of work since, and I would say it all operates in a very similar way with this sort of fixed retrospective memory windowing, or this sort of like fixed size active set. So if we want to define a projection very similar to what we had with kernel regression, I think there's a very, there's a couple of questions here. What's the right metric for computing projections? Are projections computable? And what does convergence mean here? Well, before I go into the answer to those questions, I want to define what the projection is that we propose. And it's very similar to what's going on in Polk. So basically, we take a Gaussian process posterior at time t. After you get the new data point, then you compute the a posteriori update at time t plus 1. and then that causes you to update your mean and covariance computations. And then what we say is rather than looking at a subspace of a fixed size, let's fix instead the error associated with memory reduction, right? Some epsilon neighborhood, and this epsilon neighborhood is in a specific space of Gaussian process posteriors, and then we greedily throw out points of our dictionary until we hit the boundary of this neighborhood. And what this ensures is that the posterior distribution that we end up with is epsilon close to the one whose memory increased. And then you might ask, well, what's the metric in which this posterior is computed? And we choose the Hellinger metric, and the reason for that is that it has this nice, efficiently computable form for Gaussian distributions. In particular, if you want to compare two different Gaussian distributions, nu and lambda, you just have to compare their associated covariances and means, and that's that. So that's by the Hellinger metric. And so as soon as you do that, then you can have very similar sort of a convergence versus complexity trade-offs that you have for kernel regression. In particular, you can have, oh, where's the cursor? Just finishing up the explanation of how one can compress a Gaussian process in the online setting, and how there are very similar sort of theoretical trade-offs between memory and accuracy that can be derived for this setting. And what you observe is that with these sort of compressions, then you attain experimentally very similar sort of accuracy versus complexity trade-offs as we had for kernel regressions. In particular, we take sort of the classic fixed memory techniques for compressing Gaussian processes in the online setting. And we say we fix the amount of memory they keep the amount of points that they retain as that which is associated with this sort of online compression technique. What you observe is that, so here's the number of points our model retains across time, this blue. And here's the amount, here's the sort of convergence criterion, this blue. And what you can see is that the sort of model likelihood converges to a comparable level to some optimal offline benchmark. But by contrast, right, this red one is unable to do so. And that is because the points it's retained, sort of the fixed number of points it's retained is insufficient for convergence in this case. And there's so then this sort of online performance should be contrasted with what is directly coming from the textbook definition of a Gaussian process update, where you have a dense Gaussian process and its memory is basically just growing unbounded with time. So by introducing, let's say, very specific projection steps for discerning which points from the past are statistically significant, then we can have a model that obtains a favorable trade-off between convergence and accuracy, or sorry, convergence and memory. Okay, and then once you have this, then this sort of thing can actually be directly applied to various probabilistic inference problems that come up in robotics and autonomy. So here's a situation where you have a robot and it's trying to drive around a 2D environment and basically trying to decide whether an object is one type of obstacle or another, and based off of the sort of in which interval the real value is taken, then so if it's, let's say, between 1 and 2, you say it's a chair, and if it's between 2 and 3, then it's a table. So that's basically what that's what truncated sign distance field is, and as a target variable for assigning classification labels. So you can just directly apply Gaussian processes to things like probabilistic mapping, where you want to figure out what object classes are in the environment. So this is some work that's recently appeared at IROS. Okay, and I think with that, I'm going to skip the last part and just say that very similar rules can be derived for Monte Carlo methods, but I'm not gonna have time to talk about that today. And so then, to go back to our Venn diagram from the beginning, the overall point of these works is to try to make Bayesian and non-parametric methods scalable for online inference. And the reason for that is we want to use them in sort of incremental settings, because that's important for robotics and autonomy. We want models that can stably adapt to new information, either via convexity or Bayes rule. But their complexities is a challenge. So that was the main focus on how to design projection rules that get that under control. Okay, good. So I think with that I can conclude. I've basically discussed a framework for complexity control of Bayesian and non-parametric models that, via the connection between projections and statistical tests, help you decide whether new data being observed is important. And I think there's a lot of applications of this kind of work for localization and mapping, climate forecasting, system identification of sort of nonlinear dynamical systems, various problems that arise in econometrics. And I think there's a whole lot of interesting ways that these works can be scaled up to high dimensional spaces through defining more intricate data-driven kernels, or kernels that come from time series analysis. I think with that I want to conclude and thank everyone who's been a part of this work, especially Ketan. And sorry that picture of you is a little outdated, but yeah. So with that, I'll conclude, and happy to have any Q&A.
Thanks, Alec. I think there's a question in the chat about data representation. So you can ask.
Sir, could I ask the question? Good evening, sir. I'm from IIT Kanpur, from PhD first year, from Industrial and Management Engineering Department. So I had question from the operations perspective. If we look at the complexity and its representation, so can we? I had question regarding the complexity and its representation. So can we use data envelopment analysis for representing the complexity areas? Like, we can define particular set of input and output variables, and we can define the possibility set for that particular area in order to make the interpretation more easier in the graphical manner. Like, here we are representing everything mathematically. So is it possible that we do programming, like we go for integer programming, or we go for pure or mixed IPP, or why didn't we use primitive goal programming so as to achieve these particular goals? Why we had Bayesian algorithm, even that is a present theorem, so it is also good. But when we study it from the operations research point of view, so could we use this primitive goal programming or data envelopment analysis as methods in order to represent the data?
So I think the question ends up being one about the goal of a given representation. So what I'm not sure about is when you say data envelope method or some integer programming method. I think that these methodologies are perfectly fine, but can they be used to, for example, let me go back to this very evocative picture. but can they be used to directly build a classifier, for example? I don't know how integer programming is used for that. I suppose you could do a decision tree. Is that what you mean?
Yeah, maybe a decision tree, or maybe we develop a minimum spanning tree, maybe using a Kruskal's algorithm for greedy approach. So here we have used personalization as a particular method where we are going for a greedy approach. So why didn't, maybe the complexity levels are different for both the algorithms, I guess.
No, that's a great, now I understand your point. So yeah, for sure, a decision tree or a nearest neighbor approach, clearly interpretable and well established. So I think the tricky thing about those techniques is how they can adapt on the fly to new information. To my knowledge, when you have a decision tree on data set 1 and you want to change the data set, I believe the decision tree needs a thorough retraining. Is that correct?
Yeah, at one point of time, because as you defined in your PPT or your PDF about the epsilon value, so it may happen, epsilon, have you taken it as infinitesimally small value, or what is the epsilon value? It is like, because for data envelopment analysis, when we do dual programming for a particular formulated problem, we take epsilon as a very infinitesimally small value. So that is basically a point that we are trying to search as a space for that particular dictionary, which you defined as a space in that particular
but the decision tree itself, you would have, let me go back to this picture. Oops. In this picture, right? If you had, say this is now a decision tree at time t, and now you need to make a decision tree at time t+1, you have to do a complete retraining, right? You can't just change the model a little bit.
Okay, so we are to start from the step 0 again.
Yeah, exactly.
Okay.
I think they fundamentally need offline training, at least the traditional one. So that would be the challenge there, because that training is sort of non-trivial. So that's why I think it's not suitable for runtime scale training.
Yeah, I think that is the key difference between all the various methods, classical methods so-called, and the online methods, which is that you don't need to retrain your algorithm for the whole of the data set each time a new point arrives.
Okay, so it is basically we are focusing that if for a certain particular change, we can avoid this particular entire steps, and
yeah,
exactly.
Okay, so it would be like its application would can be anywhere in operations research, like if we are calculating the efficiency of a particular organization or any particular firm. So in that case, then we need to define different decision trees. Then we make a spanning tree for that particular case. Like it's maybe a transportation problem, for say, like logistics problem. So like every time we need to search. So I guess this method would help us to reduce that particular amount of steps, 0 steps again, that we initially needed when we are doing it manually or.
Yeah, exactly. You could ask the question, how is my data changing with this sort of approach? You know, to use a operations research term, it helps you keep a finger in the air, right? Feel which way the wind is blowing a little bit more than an offline model.
Yeah, thanks. I hope that clarifies. Any other questions?
No, so not from my side. Thank you so much for clarifying the doubt.
I think the operations. Great. I think the operations research perspective is fresh because like both of us are not from that area. But maybe if
Okay,
you are
maybe, and
you can
I'm
guide
not at all related from the electrical background because my BTech was also from industrial engineering. So my perspective of thinking is entirely from the operations background. So, but still, I got the few points that how we are avoiding the complexities by not going to again restart, and then we are directly just changing that particular node that is denoted as epsilon, and then we again reframe the same minimum spanning tree and we go on further with it. I guess that was the idea which you were trying to explain.
Yeah, I think it actually could be very interesting, especially, I mean, here in the US, everyone is up in arms about power pricing. I think it could be very interesting to try to do a case study where you look at supply and demand historically and try to like identify statistically significant fluctuations, you know, and in an incremental fashion. I don't think that this is done today just due to the I don't know, implied volatility of such an approach, right? Like they need some stability in the pricing mechanisms, but clearly there are some tail end cases where that breaks down, like Texas last month that now everyone's talking about. So it could be very interesting to figure out what are the sort of like interesting long range dependencies, and I think applying a method like this would help you pick out those sorts of things. But maybe there are some other instances that would arise in supply chain or logistics that would be useful. For example, certain demand patterns are very much seasonal. So clearly everyone in the US goes shopping in December for Christmas. I mean, not me because I'm Jewish, but like most Americans. And, you know, there must be something similar in India. So I think that there could be some very interesting ways to try to pick out those sorts of incremental fluctuations in a sort of pricing or logistics type problem. So I think that's where I see the connection.
Sir, I had one more doubt. Sorry to interrupt. Regarding the queuing theory, which we use, like you had this particular mathematical model. It was an infinite mathematical model. So when we, it was the infinite mathematical model, I guess that big equation which you discussed with where we can find mu and v. So in that, I had a doubt, like as you just discussed about the dynamics of price changing. So if we are going for a queuing theory model where initially we take finite, but if the case is large, we take infinite population. So in that case, how this particular Bayesian theorem would be helping out? Because in that case, suppose if we are trying to implement a queuing system for any hospital or for maybe any sort of firm, it can be anything. So how would that be helpful in this case?
Yeah, that's great. So the queuing theory model is typically associated with a Poisson process, correct?
Yeah. So it is like we have a fixed arrival rate, fixed service time for one particular service which is being provided. So in that particular case, we would be having like for the input, like that is the incoming or the arriving time would be forming a one sort of spanning tree, and the service time would be forming another spanning tree. So then in that particular condition, how would we be defining the epsilon or the space which you were discussing about?
Yeah, that's a good question, actually. I think the models I am defining are ones associated with, I mean, what do you call it? The population distribution is infinite dimensional, but the sort of like finite incrementally updating one is finite dimensional. So what I'm trying to do is generate approximate incremental ones that eventually get close to the population infinite dimensional one, but their memory is always under control. So I think in the Poisson process situation, you typically have these Poisson points that you need to evaluate in order to construct your likelihood model. And the number of Poisson points across time increases, I believe. Is that true? So in this case, you would try to only keep some statistically representative subset of past Poisson points such that in the limit, it will never become infinite dimensional, but it will become close in some statistical convergence criterion to the infinite dimensional one.
So, sir, as per what you said just now, so if we are introducing some particular hypothesis for different conditions, a null hypothesis like 1, 2, 3, 4 till 10, and then another hypothesis. So in that case, could we reduce the complexity of the particular problem? Like you just said, the statistical approach. If we are stating some hypothesis for one particular method, maybe the null hypothesis have 2, 3, 4 variants. So would that simplify that particular problem's complexity?
With 1, 2, 3. I didn't understand the point 1, 2, 3, 4 variants.
Like, no, I'm just saying, suppose I have a hypothesis. Like I have a null hypothesis that this particular thing, this particular minimum spanning tree is true. Initially, we assume that the spanning tree is true, and then we have null hypothesis 1, another hypothesis as H1, that this null hypothesis is not true because of particular condition A. Then we have second hypothesis that this particular minimum spanning tree will be only true if and only if we follow hypothesis number 1, or likewise if they are forming multiple loops, because null hypothesis is like we consider the minimum spanning tree as to be true. So when we go to other hypothesis methods, so what if they form a loop?
This I'm not sure. Are you talking about some algorithm which is using this hypothesis?
No, I'm just not talking about the algorithm. Sir just discussed about the statistical area, like how we can statistically also represent this particular minimum spanning tree. So like in order to reduce the complexity, if we are using any sort of hypothesis so that we can more properly formulate the problem in small subpoints instead of a big particular problem. Like for
not clear. So basically you have to ask in such a way that we also understand what you are talking about.
Okay.
Right? So I'm not able to understand.
I think what you're saying is somehow you have a bunch of different spanning trees. You have like 5 different spanning trees, and you switch between them according to some conditional statements, right?
Yeah, like in
I
between
feel
we have too many
fine, but it's a very different context.
Yeah, I don't
like one can do that. I don't know how I don't know how you would establish, for example, any sort of consistency of such a model. I think that is quite a different technical question than what is being posed in this work. It's an interesting one, but they're just quite distinct. So I wouldn't want to say anything foolish, and because of lack of understanding about how the analysis of decision trees goes.
Because when we are actually applying the queuing theory models, then we face a lot of complexity issues due to the infinite population size. So then we from the statistical background, if we consider different hypotheses. So in that particular hypothesis, if we consider one hypothesis, we draw a one spanning tree for it. Then that is for null hypothesis. Then we develop different hypotheses on the basis of the null hypothesis. So all that hypotheses have different spanning trees. So that likewise the problem initially is so much complex that it needs too much of uh, recursions or too many iterations in order to solve it, and that's pretty large. So how will this method help?
What is this problem called?
This is a queuing theory model. So we have in this, suppose if we take example of a hospital where just for a day, if we don't know the amount of people coming to the hospital, and then the amount of service time which is required, because every patient has a different service time and every patient requires more amount of discussion with that particular doctor. So we cannot just really define that how much time one patient would take. Many times the patients don't report actually to their appointments made, or many times there is some gap between the service time and the patients need to sit longer. So few patients are following a greedy approach. Like if they are going to.
Just, you were explaining queuing theory, but I was asking about that, talking about spanning tree, right? Spanning tree are not applied to queuing theory.
Sir, spanning tree are not applying to queuing theory. That's I know. But spanning tree in the sense is like if we just take the set of the arrival time population, if we just differentiate the two service and arrival time and their populations. So for that different populations, we need to define something, some variables. So is it possible, like if we use a minimal spanning tree for defining that particular set of arriving patients or maybe arriving people, and this another spanning tree of people where we have provided the service, and then how could we merge both of them so as to get a confined model? I guess
Yeah,
is that
I don't know what you're talking about.
I think where the rubber meets the road is through the Poisson process, right?
I mean, I'm just trying to mix two concepts. We don't initially use minimal spanning tree in queuing theory, but in order to reduce the complexity, I'm talking from the complexity perspective, because when we have infinite population from both the sides, then somewhere we need to reduce the complexity part. So like, how could it be applicable? So my major question was
I think the point is that rather than introducing the decision trees as a computational approximation, you try to keep the original probabilistic model in the form of a Poisson process and just directly go for some efficient representation of that Poisson process based off of the data you're experiencing. So I think it's just a different avenue to pursue. I don't see how what this work is saying has any particular bearing on the design of decision trees itself at this time. Does that make sense?
Yeah, I'm trying to understand a bit, but
so I'm going to send you a work. I think you'll have a different opinion of it than me, as someone who comes from queuing. I'm just going to send it on the chat because why not? Where is the chat function? I think I have to stop the video for the chat to come. Okay.
Actually, sir, technically we don't use minimal spanning tree concept with the decision making tree concept, but what if we are trying to merge it? That was my particular question. So as to reduce the complexity in the advanced decision models, which we directly use as a part of application. So
you can have a look at the paper in the chat. Huh? That one is
okay. Oh,
Poisson.
Yeah, this is a very nice paper where they talk about how you would try to directly model a Poisson process using kernel methods. And I think a rigorous study of the implications of this direction in the context of queuing theory is not done, actually, or you know, is an open research question. So I think it could be very interesting to compare how would this sort of piecemeal decision tree approximation contrast with some sort of non-parametric representation of a Poisson process. I don't know, right? But these are questions to ask. So I think this is the question maybe you didn't know what you were asking, but that maybe is revealed through this discussion.
Actually, I had this question out of curiosity because a few months back we had a seminar on queuing theory. So they had infinite population from both the sides. Then I thought over that particular point. So today the seminar was on how we can reduce the complexity part. So that's why I had this particular doubt. Like in that also we have a lot amount of complexity due to the infinite population. So that was my point of asking the question, like how could we reduce it using this particular algorithm? Still, it is not explored one. This is the problem from my curiosity, which I came out. And how could we approach if that is a particular situation?
Yeah.
Okay. I think there's one more question in the chat. You can just have a look.
Yeah. So Abhishek has asked, how is a one-layer neural network with pointwise nonlinearities being your kernel evaluations at different training examples, is that related to a neural network? Yes, it is true that kernel regression or Gaussian mixture models, whatever you want to call it, can be connected to the theory of neural networks in the sense that they both satisfy some universal function approximation properties. And therefore, it's possible to show that if you have a neural network of some depth, then you can find an equivalent one-layer neural network that is way taller, right? So, and as that height, or I guess they call it width, but I prefer to call it height. As that height goes to infinity, then there's some equivalence between them. And actually, there's been some work that there are specific choices of kernel that make that function approximation error as small as possible. This is called the neural tangent kernel, I think put forth by Sanjeev Arora at Princeton. But I think the tricky or unsatisfying thing about this analysis is that you need the width to go to infinity, which is sort of impractical. So what I think makes much more sense is if you have a neural network with capital L layers, how did you get there? How did you decide that you needed L layers? And I think kernel methods provide a potential path forward for addressing some of those very sort of pesky NP-hard questions of neural architecture search. Because you could imagine if you run kernel regression, let's say with some sparsification until convergence, right? And you could say, okay, well, now I want a more, what do you call it? Now I want a richer function representation. So I should, what do you call it? Add another layer, right? And then retrain with some modified definition of your kernel. So I think this is I think going from kernel to neural network conceptually makes more sense than going from neural network to kernel, except that going from neural network to kernel is just like a way for providing some theoretical justification for a lot of mysterious things about neural networks. But one thing that is still persistently mysterious is how do you decide which architecture to use? So yeah, I don't know. That's just my opinion about this connection. But definitely there's a deep and interesting bridge between these two choices of representation.
Yeah,
yes.
Thanks, Alec.
One more question about localization and mapping. So I only talked about the mapping application a little bit, but why don't I share? So mapping is a situation in which the input variable X is associated with some sensory observations. So think like your visual field or acoustic measurements or something. And from that, you try to discern attributes of the environment, like whether there's obstacles, walls, open field, etc. And so the question is, I mean, it's obvious what the feature space is, but what is the target variable? And so there are a number of different ways to do that. In the particular example that I was talking about, we were using this thing called the signed distance field, which is an entity that comes from a famous work of Dieter Fox. Let me see if I can find it. I'll just send you my work because that has the references a little bit more. Give me a moment. Yes. So in this work, we sort of define how the signed distance field works and how to use sort of XY pairs in this context to construct a probabilistic map. But the map doesn't have to be probabilistic. We did Gaussian processes here because we were explicitly focused on uncertainty representations, but you could easily just do kernel regressions, or you could use a Bayesian neural network. There are a million different things you could do once you have the data in the format that is appropriate for mapping. For localization, right, I agree that I shortchanged that aspect as well, or maybe even skipped over it. That was emphasized more in the last part of the talk, where I sort of skipped over related to Monte Carlo methods and importance sampling. But the reason localization comes up in there is because Monte Carlo localization is a sort of canonical technique for localization. So you might ask, okay, well, what is localization? Again, the state variable ends up being some sensory measurements, and the target and the target variable in that case is typically some range measurement, which tells you, for example, approximately how far are you from an object of interest. So then, you know, you can set that up as a regression problem. Now, people study Monte Carlo methods for this problem rather than just doing vanilla, for example, least mean squares, often because the distribution of, let's say, possible outcomes for where a source signal might be is often multimodal when you're in, for example, a cluttered or a cluttered environment, or like an urban environment. Then there's a lot of interference, and this causes there to be multiple possible signals that you can hone in on for figuring out where the source is that you're trying to localize to. So I recommend there's a famous book called Probabilistic Robotics, and it has a chapter on Monte Carlo localization. And I recommend reading that, and then it would be a little bit clearer what I'm saying about why important sampling comes to bear on this problem. Is that clear? Partially satisfying answer.
I think it's a good answer. Like that, particularly Monte Carlo localization is quite a good link with this one. Yeah. Okay, so are there any other questions from the audience?
Sir, I had one more question about the optimality which you mentioned in your PDF. So why are we looking at from the Pareto efficient frontier, like Pareto optimality is the major concern, and or we are just following the Monte Carlo simulation for that particular part? Like you just discussed for the localization part as Monte Carlo. Could we also use like Pareto optimality point when we are discussing about the optimality for that particular complexity in terms of maybe it may be linear, it may be non-linear, it is non-parametric as mentioned in your PPT. So from that perspective, how could we measure the optimality?
This is a single objective problem, so
yeah, I think maybe your question applies more to the Bayesian inference question, where you might ask, okay, rather than looking at a distribution of outcomes, why not make it scenario based and define a cost for each different scenario? I think that's what you're saying, but I might be misunderstanding.
Yeah, for different scenarios, like so the optimality frontier, like how are you defining that particular optimality frontier as you mentioned in your slides?
No, this is a single objective optimization problem.
Yeah.
Okay, fine. So, okay, that was my point. So we cannot go for data envelopment analysis because we have just a single objective.
Yes.
I guess maybe that's the reason what I'm having a question in my mind and it's not matching. Maybe, okay, it's a single objective. That's why, okay.
And in the situation with a probabilistic model, right? Even then, there's still only one sort of probabilistic objective.
Maybe due to that single objective, you didn't prefer any sort like goal programming approach, because we need multiple objectives for that in order to achieve that particular goals. Maybe the single objective model might be a particular sort of constraint, rather, I must say, for not using these techniques. Maybe one of the constraints. Like what I was discussing was for multi-objective approach. Maybe that particular reason maybe that particular reason we are using here a linear model or a non-parametric model.
Yeah, I'm not sure there's a question in there.
I'm just saying that the parametric model that non-parametric model you used was because of the single objective point, I guess. Because in one of your slides you mentioned about the goal was to achieve was to lower the complexity point.
No, that is not the reason. Single objective is the problem. Non-parametric model is the approach.
Okay, parametric model is the approach. So then why didn't we use here primitive goal programming? Because in
every algorithm cannot be used for every problem. For every problem, there is an optimal algorithm, right?
Yeah.
This is the optimal algorithm. You cannot say that why didn't we use that algorithm here? It doesn't work like that, right? For every algorithm,
I'm not saying about your work. Your work is excellent.
No.
I'm just saying from the operations, my research perspective, like in my higher studies, how it would be helpful for me.
Obviously, you don't apply goal programming to every problem that you see.
Yeah, absolutely. It's not
No,
to every problem that we see, because we need a number of constraints in order to form a goal programming model.
Sure.
Yeah, that's.
But I think the point is that those are not incrementally adaptive, right?
Yeah.
We clarified this. Yeah.
Maybe that particular reason is why this many methods were eliminated. Maybe.
Yeah. And I don't think that those.
None of those.
None of those. Yeah. Maybe that incremental point. May be the main reason, I guess, that Bayesian theorem that you have explained is more in use. Okay.
Okay, I think that's right. Yeah. Okay, so any other questions from the audience? Okay, if not, then thanks a lot, Alec. It was a nice talk and good discussion.
Yeah, appreciate the invite, yeah, I think if anyone wants to have ongoing discussions about how this work could be used, or potential avenues to pursue, I'm happy to correspond via email. So don't hesitate.
Sure. So thanks. Okay. Thanks a lot, Alec. Bye.
Take care. Bye.